Welcome to the Advanced Research Complex. My name is Carly Cran and I'm a research scientist with the Andre E. Lalonde AMS Laboratory. The Advanced Research Complex was finished around 2014. It's located on the University of Ottawa campus, and we're well situated here with a phenomenal machine shop and electronics shop in support of the equipment that we design and build in-house. And the Advanced Research Complex itself was custom built around the accelerator mass spectrometer. So when you enter the building, there's a glass wall and you can look in and you can see the glory of the AMS with the chart of the nuclides across the floor. And people are always curious what we do inside that lab. So it's my pleasure to bring you in and give you a tour.
My name is Liam Kieser. I'm the director of the Andre E. Lalonde Accelerator Mass Spectrometry Lab. Here is a picture of Andre Lalonde, who was the Dean of Science at the time when the funding came through from the Canada Foundation for Innovations for this accelerator mass spectrometer. We didn't have really a home on campus, and the genius of Andre was that he found there was another CFI, mixed the two groups together, the physics laser group, and now we have this marvelous building called the Advanced Research Complex, and it has an accelerator mass spectrometer as a rather prominent place in the entrance to this building.
We'll start our tour upstairs on the 4th floor, where we're going to meet with Sarah Marcelli, our lab manager, and she's going to walk you through how samples are processed in the lab.
My name is Sarah Marcelli. I'm the laboratory manager at the AE Lalonde Radiocarbon Prep Lab. I work with all sorts of different material types in helping to prepare them for analysis on the AMS. All sorts of different material types, from ivory to bone, shells and wood. We also do environmental analyses, water and gases, and there's other different radioisotopes that our lab can process, but today I'll be talking a little bit about what we do in the radiocarbon lab. So typically archaeologists, they'll submit organic materials. The first stage once they come into the lab is we do some physical cleaning, pre-treatment. So we would scrape the exterior off of wood sample, charcoal, try to remove any rootlets, and target just the material that we're interested in dating. Second, we might apply a chemical pretreatment, where we would, for wood samples, an acid treatment, and that would help remove any foreign materials that we don't want to analyze. So carbonates or mobile organics. For wood samples, bone samples, they go through a collagen extraction. So we're interested in the collagen in the bone. That's a 4-day process where we basically leach the carbon out, the collagen out of the bone sample. And that's what we target for the analysis. Following chemical pretreatment, once the sample is fully cleaned up and we're just targeting the piece that we're interested in dating, the sample would go through combustion. So we convert the solid material into gaseous CO2 in purified form. So that would be stored in a glass ampule under vacuum, quantified and cleaned up. So all of our samples go through this stage to CO2. Once they're in CO2, they get converted to elemental carbon or graphite using an iron catalyst on our graphitization lines. Those are custom built in-house. We designed it and built them here at the University of Ottawa. So this graphite is what ends up in the accelerator, ultimately, on the AMS, and that gets pressed into what we call a target. So all that small amount of carbon that we're producing, about 1 milligram of carbon, gets pressed into this target, and that's what gets loaded on the AMS. That's what we measure. At the graphite stage, when we convert the sample from gaseous CO2 into solid form, which is what gets measured on the AMS. We put it through what we call a hydrogen reduction process. So the CO2 is reduced to graphite, elemental carbon, and that happens at the temperature of 550 degrees. We use custom-built ovens to control that reaction, and hydrogen gas, and that converts to carbon plus water. And we scrub the water out on a water trap and produce graphite on an iron catalyst. What we're looking to measure in the sample will tell us how much time has passed. We can measure back about 10 half-lives, which brings us to just over 50,000 years. So we take the raw material that comes into the lab, clean it up, physical cleaning, removing any contamination from the exterior, chemical treatments if needed, base acid washes or collagen extraction on bone. Following that, we combust the sample to CO2, purified gas. Once it's in that stage, we can graphitize. So we convert that gaseous CO2 to elemental carbon, graphite, and that's what gets measured on the AMS.
So upstairs on the 4th floor in the prep lab, the samples are, the final stage is these targets, and they get loaded onto bases. And then we take 200 of them, including all the standards that are associated with those batches, and we load them into a sample wheel. That sample wheel is then loaded into the ion source of the accelerator. And in the first stage of the accelerator, what happens is we go from a solid sample into an ion cloud. And in that ion cloud, we have many different isotopes. And what we're concerned about is carbon 14, 13, and 12. And we need to separate out those 3 isotopes because they're measured slightly differently. So in the first stage, we call this the low energy end of the accelerator. We have a magnet that separates carbon 14, 13, and 12, and they're accelerated through the AMS. And right in the middle of the big tank, we have a canal that's full of argon gas. And we shoot 3 million volts of electricity into that argon gas, and that blows up molecules. And that's important because we're interested in carbon 14, but you could have a carbon 12 with 2 hydrogens on it, and it will have the same mass as carbon 14. And in the end, all we're measuring is the mass of an atom. We don't know if it's carbon 14, nitrogen 14, or a carbon 12 with 2 hydrogens. So we have to get rid of those things that have the same mass. So that's what happens in the accelerator is you get rid of the molecules, the molecular interferences. When you exit into the high energy side of the accelerator, we have a fairly clean beam. And we have our 3 isotopes of carbon that are going through separately. They're being bounced through one at a time. 12, 13, 14, 12, 13, 14. The carbon 12 and 13 are abundant isotopes. They're the stable isotopes. Carbon 12 is the one that you see on the periodic table because it's over 98% of all carbon is carbon 12. So it's the most abundant. Carbon 13 is not nearly as abundant as 14, but it's still much more abundant than carbon 14. And that's important because we measure them differently on the accelerator. So with these big beams of carbon 12 and 13, we just measure the total size of the beam, and then we convert that to the number of atoms. Carbon 14, there's so little of it. It's like 1 grain of sand in a huge beach. It goes down to the very end of the accelerator, and the individual atoms are counted one at a time. And so when you go into the control room and you look at the software that we use to control the accelerator, you can see a little plot, and we watch the individual atoms of carbon 14 as they come in. The calculation of a radiocarbon date is essentially the ratio of carbon 14 to carbon 12. And when you're living and breathing and when plants are photosynthesizing, you're incorporating modern CO2 at a certain ratio of carbon 14 to 12. And then when you die, or when a plant dies, then the carbon 14, which is an unstable atom, is going to start emitting beta particles and decaying and breaking down. It actually turns back to nitrogen 14. So your ratio that was once in line with the atmosphere starts changing, and you have less and less and less carbon 14 as something ages. It has a half-life of 5,730 years, which means after 10 half-lives, there's so little carbon 14 left that makes that puts the limit on radiocarbon dating at 50,000 years. So this 3 million volt accelerator is used for more than just radiocarbon dating. We measure isotopes from hydrogen or tritium all the way down to uranium, very heavy elements. So that's why this accelerator is so big. We are very excited to be announcing that in the fall of 2021, we will have a new accelerator mass spectrometer, and it's called a MCADIS, which stands for Mini Carbon Dating System. The MCADIS is the top-of-the-line technology for radiocarbon dating. Ours will be, there's something like 30 of them in the world currently, and the unique thing about the MCADIS is that it's tuned just for radiocarbon, and so the efficiency is very high, and that means we can date smaller and smaller samples. Currently, on the big machine, we're tuned for about 1 milligram of carbon. So if you're working on a wood sample, we need to start at about 10 milligrams of sample. With the MCADIS, we can start much lower than that. But then that puts the onus on the archaeologist, because you have to really know what you're dating and why and what time that carbon is going to represent. So if you're dating an individual seed, you need to know what that individual seed is going to tell you. Other things that we'll be able to date are forams, very small forams from marine cores. We could date museum specimens that were previously too precious to have destructive analyses done on them. Human bone is another one, because we have to be very sensitive around how much material is taken from a human bone. So we're going to have many new capabilities with this mini carbon dating accelerator. And we'll be able to do things like dating individual compounds or isolating things like DNA for radiocarbon analysis. So it's going to be a very exciting decade, I hope. One of the other foundations of the lab is training the next generation of scientists. So on campus, we invite students from our science classes or other backgrounds in science to come into the lab and either take tours or process samples, learn a little bit more about what we do in the lab, the physics side as well. We have students from physics. And we also have a training program for archaeologists and other researchers that use the facilities here. And they can come to the lab and process their own samples with hands-on training from one of our specialists here in the lab. And so we have a slogan: our doors are always open. Please don't hesitate to contact us if you'd like to take a tour, either for now virtually, but hopefully soon in person.